This shape contains infinite detail. Watch what happens when we zoom in, forever. Everything you're about to see comes from one line of math. No tricks, no hidden images, just a single equation repeated in the strangest object ever discovered. This is the Mandelbrot set. To most people it looks like a bug, or a snowman tipped on its side, or a strange black island floating in a sea of color. But mathematicians call it the most complicated object in mathematics, and they mean that almost literally. Its edge is infinitely long. Its detail never runs out. You could zoom in for the rest of your life and never see the same thing twice. And yet the rule that creates it is so simple you could write it on your thumbnail. So how does something this simple become something this infinite? To understand that, we have to start with a very strange kind of number. Every number you've ever used lives on a line. Whole numbers, fractions, negatives, line them up and you get the number line. But there's one question that line can't answer. What number multiplied by itself gives -1? Positive times positive is positive, negative times negative is also positive, so nothing on the entire number line works. For centuries mathematicians said this problem had no solution, and then they did something audacious. They invented one. They called it I, the imaginary unit, defined by a single property I times I equals -1. It sounds like cheating. It turned out to be one of the most powerful ideas in all of science. Once you accept I, a new kind of number appears, a complex number. It has two parts, an ordinary part and an imaginary part, something like 3 plus 2i. And here's the beautiful move. If a normal number lives on a line, a complex number lives on a plane. The ordinary part tells you how far to go left or right. The imaginary part tells you how far to go up or down. So every complex number is really just a point, a coordinate on a two-dimensional map. This map is called the complex plane, and it's the canvas the Mandelbrot set is painted on. Every point you'll see is one complex number, waiting to be tested. Here's the entire rule. Take a point on the plane, call it C, then follow these steps. Start with 0, square it, and add C. Take that answer, square it, and add C again, then again and again forever. That's it, square, add C, repeat. This little loop is the engine that builds everything. Let's try a general point. C equals -1. Start at 0. 0 squared plus -1 is -1. -1 squared plus -1 is 0. Then back to -1, then 0. It just bounces between two values, calm and trapped forever. Now watch a different point. C equals 1. Start at 0. 0 squared plus 1 is 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5. 5 squared plus 1 is 26. Then 677. It's exploding. In just a few steps it races off toward infinity and never comes back. And that is the only question the Mandelbrot set ever asks. For a given point C, when you run the loop, does the answer stay small and trapped forever, or does it escape to infinity? If it stays trapped, the point is inside the set. We paint it black. If it escapes, it's outside. Two destinies, trapped or free. That single yes or no question, asked at every point on the plane, draws the entire picture. But how do we know a point is going to escape? We can't actually run the loop forever. Here's the elegant part. There's a boundary of no return, a circle of radius 2 around the center of the plane. It's a proven fact that if the value ever steps outside that circle, even once, it is doomed. It can only accelerate outward from there. So we don't need infinity, we just watch. If a point crosses radius 2, we stop and label it an escapee. If it's still hanging on after hundreds or thousands of steps, we treat it as trapped. That single threshold turns an impossible, infinite question into something a computer can actually answer. So let's ask the question everywhere. Imagine sweeping across the entire plane point by point, running the loop on each one and asking trapped or escaped. Color every trapped point black, and slowly, out of pure arithmetic, a shape condenses out of the void. A round body, a perfect circle stuck to its side, smaller and smaller buds all around the edge, a long spike reaching to the left with its own tiny buds, and scattered out in the emptiness, miniature islands, echoes of the whole. No one designed this, no one drew it. It was always there, hidden inside the equation, waiting for someone to look. Now for the color, because the color isn't decoration, it's information. For every point that escapes, we simply count how many steps it survived before crossing that circle of radius 2. A point that blows up almost instantly gets one color. A point that clings on for 20 steps gets another. One that lasts 100, another still. Map those counts to colors and the black island bursts into flame. Bands of color ripple outward like contour lines on a map, each band marking points that all escaped at exactly the same speed. The bright churning colors are the exterior, the points that ran away, and the closer you look to the black edge, the harder those points fought to survive. That edge is where everything interesting happens. Let's name what we're seeing. The big heart-shaped body is called the cardioid. Every point inside it shares a destiny. The loop settles down and homes in on a single value, like a marble spiraling to the bottom of a bowl. The large circle attached to its left is different. Inside it, the loop doesn't settle on one value. It locks into a rhythm, bouncing between two values forever, a cycle of period 2. Every bud around the edge has its own rhythm, period 3, period 4, endlessly on. The interior isn't empty, it's a map of every possible stable cycle a point can fall into. And separating the trapped rhythms from the escaping chaos is a single, razor-thin line, the boundary. This boundary is the Mandelbrot set's true miracle. Everything you've seen so far is just the setup for what lives here. Think of a coastline. From space it looks smooth. Fly closer and bays appear inside bays. Closer still, and every rock has a jagged edge and every grain of sand has an outline. A coastline gets longer the closer you measure it. The boundary of the Mandelbrot set is that idea taken to infinity. It is infinitely crinkled at every possible scale. Its length isn't large, it's literally infinite. And unlike a real coastline, it never smooths out and it never simplifies. There is always more. So let's stop describing it, let's go in. We're heading for the valley between the body and the head, a region mathematicians nicknamed the Seahorse Valley. Watch the edge unfurl, curling tendrils, delicate spirals winding into spirals. Every one of these shapes is made of the same two kinds of point you already understand. Trapped and escaping, ranged in patterns no human hand could plan. And we've barely begun. We've magnified the image about 100 times. Keep going. Deeper, the spirals give way to branching filaments like frozen lightning or the veins of a leaf. We're now 1,000,000 times deeper than where we started, and then, look at the center. There it is again, the whole shape. The body, the head, the buds, a complete, perfect Mandelbrot set buried miles inside its own boundary, a copy of the entire universe we started with, tucked into one of its own crevices. How many of these are hidden in here? The answer is infinitely many, and every single one has its own infinite coastline, with its own infinite copies inside that. Let's talk about how deep we can actually go because the numbers stop making sense. Suppose we zoom until the original picture would be as wide as the entire observable universe. At that magnification, the little region on your screen right now would be smaller than a single atom inside it. That's a magnification of around 10 to the 42. And here's the part that breaks the mind. Mathematically, we are nowhere near the bottom. People have zoomed to 10 to the 100, 10 to the 1,000 and further, and the detail is still there, still sharp, still endless. There is no bottom, there never will be. The complexity doesn't run out because it was never stored anywhere. It's generated fresh at every depth by that same tiny loop. Now, those hidden copies come with a subtle twist. They are not perfect clones. Each miniature Mandelbrot is unmistakably the same shape, but it's dressed differently. It's wrapped in the swirls and spirals of whatever neighborhood it lives in. A mini brot in the spiral region wears spirals. One near the lightning wears lightning. Mathematicians call this quasi-self-similarity. The big pattern repeats, but never as a lazy copy-paste, always remixed by its surroundings. It's the difference between a fractal and a mere repeating tile. The Mandelbrot set doesn't just repeat itself, it revenants itself, at every scale, forever. There's a secret hidden inside every single point of the Mandelbrot set. To see it, we need its twin. For any point C you pick, you can build a second fractal called a Julia set, using almost the same loop, but letting the starting point vary instead of C. Every point on the plane gives you a different Julia set, an infinite family of them. And here's the connection that stunned mathematicians. Move your point C around inside the Mandelbrot set, and its Julia set is a single connected piece, but the instant C crosses the boundary to the outside, its Julia set explodes into an infinite cloud of disconnected dust. So the Mandelbrot set is secretly a catalog. It's a map of which Julia sets hold together and which ones fall apart, two of the most beautiful objects in mathematics, and one is the table of contents for the other. Underneath all this wildness, there's a shocking amount of order, and it connects to ideas you'd never expect. Look at any bud on the edge and count the little antennas growing out of it. That number isn't random. It's exactly the period of the rhythm inside that bud. how many values its loop cycles through. A bud with 3 spokes cycles through 3 values, 7 spokes, 7 values. The shape is literally counting for you. And it gets stranger. Travel along the edge from the period 2 bud toward the period 3 bud, and pause at the biggest bud in between. It's period 5. 2 and 3 gives 5. Keep going, and the biggest buds follow the sequence 2, 3, 5, 8. 13. The Fibonacci numbers. A shape built from a loop about complex numbers is quietly reciting the same sequence you find in sunflowers and pinnacones. Nobody put it there. It falls out of the math for free. 2 more facts, and these are the ones mathematicians had to prove because they seem impossible. First, remember those tiny islands scattered far out in the color looking completely separate from the main body? They aren't. Every one of them is joined to the mainland by threads so impossibly thin they're invisible until you zoom in. In 1982, 2 mathematicians proved that the entire Mandelbrot set is a single connected piece. Nothing is truly an island. It all holds together. Second, how crinkled is that boundary really? A smooth line has dimension 1. A filled square has dimension 2. In 1991, it was proven that the boundary of the Mandelbrot set, a line with 0 area, is so infinitely wrinkled that its dimension is exactly 2. A curve so complex it's practically trying to become a surface, that is as complicated as a boundary in a plane is allowed to get. For all of this, the shape still keeps secrets. There's a famous question whether the set is what mathematicians call locally connected, that has resisted proof for decades. Some of the sharpest minds alive have tried, and it's still open. We are looking at an object we do not fully understand. And the person who first showed it to the world, his name was Benoit Mandelbrot. Working at IBM around 1980 with early computers, he generated the first crude pictures of this set and realized he was looking at a new kind of geometry. He called these shapes fractals, from the Latin for broken. The mathematics beneath it reached back decades earlier, to Gaston Julia and Pierre Fatou, who studied these loops by hand, with no way to ever see what they'd found. They were exploring this exact landscape 100 years ago, completely blind. It took the computer to finally turn on the lights. So what is the Mandelbrot set really? It's a single line of arithmetic, square, add, repeat, that contains more detail than the entire universe has room to store. It's proof that infinite complexity doesn't require a complicated cause. Simple rules, repeated without end, are enough to build something no mind could ever fully map. There's something almost unsettling about that. This object wasn't invented, it was discovered, sitting there, complete, inside the number system, long before there were humans or computers to find it. It would exist even if we never had. Every zoom we just took and every zoom we didn't, the infinite ones we'll never reach, they're all still in there waiting, exactly where they've always been. If this rewired your sense of what math can be, subscribe. This channel is a long, slow zoom into the ideas that do exactly that, and tell me in the comments where should we point the camera next.